the main topic that we'll discuss is labels and annotations, and how is that we deal with them in the machine learning pipeline when they are far from perfect. This is a joint work with a number of people, and I'm sure I'm forgetting names in there, but mainly people from Bristol, collaborators in Madrid, in Netflix, and in Kent University. So the first thing that I wanted to put side by side are labels and predictions and their role within the standard machine learning pipeline. So I've divided the pipeline into two, just to separate the two parts of the talk. But on one side, on the left side, we have a human, potentially a machine, that is the source of labels that together with data will allow us to learn. And that will do in this block here in the machine learning classifier that hopefully will produce useful predictions. Recently, in the last 5 years or so, there has been more and more interest in expanding that pipeline to incorporate something else, to try to address concerns that humans might have, and to ask for explainability that usually starts with the machine learning classifier that is given. And we need to provide something back to the user that reassures that the right thing is being learned. So that I'm summarizing here with this box that contains an explainer. The explainer, again, as with the human before, can be either a machine, actually a machine learning system, or a human again. And the output would be explanations that hopefully are human understandable, although in most cases they're still not. So I'm going to start by introducing the first part of the pipeline and how is that we deal with imperfect annotations and imperfect labels there. So because this is visual intelligence, I just thought that I would try to focus as much as I can in examples to do with images. And one that I particularly like, that I've used many times in the past, is the a problem of trying to assign captions to faces when they are given in the format that you can see in this image. So we have an image that contains 3 people, and we have 3 possible names that could be attached to any of the 3. So there is clearly information in there to solve this task automatically, but we are not in the normal supervised paradigm where for each instance we have a label. So there is some ambiguity here. There is some vagueness in the way that things are defined that we need to address. The interesting thing is that this will allow us to learn in settings that are far from perfect. And one could argue that a problem like object detection or face recognition or image classification is really well solved using CNNs. But whenever you change the rules of the game, like here, that there is no pairs of instance and label anymore, then the CNN requires some extra thinking to get it to work. The as Michael was saying, we are also very interested in healthcare applications, and I'm showing here an example of the work that we do with the hospital in Bristol to try to predict discharge in the intensive care unit. So there we measure a number of variables to do with the vitals of each patient. And when you plot them in 2D, they look like the clouds that you have in there. So the left one is from Bristol. The right one is from a hospital in Boston. But in both, patients that are ready to discharge are in green, and those that are not are in red. And our task is to be able to identify them. For that, the clinicians and the doctors at the hospital, they record a flag in the database that says that a patient was ready to be discharged. However, that is really, really, really noisy. So we can still use it as a target to learn, but we have to accept that that might not be always to do with the physiology of the patients, but maybe with the availability of beds elsewhere in the hospital, or with the time of the day, because they tend to make decisions at given times, but not continuously during the day. So those labels, those annotations are noisy, and we can ignore it and just train a classifier, and we've done that in the past. But it is suboptimal, and we can do better if we take this information into account. Another example is to do with the work that we do with patients with dementia. And in their homes, we deploy smart technology so that we can follow them around the house. And we do this for months to try to understand how they move, and how by analyzing movement, we can observe progression of the disease over periods of months or years. So here we also have annotations in the form of presence sensors in rooms, for example. But again, those, especially if they are light-based, they can return false positives if the conditions are not what you expect in terms of illumination. So then you have labels that are telling you that someone is in a room when they are actually not anywhere close to it. But the task here remains trying to identify where a person is in a home. And we tend to have two people in each house, so one with a mention and one that is a control. And we try to analyze how they behave differently. But again, if we don't take into account that our labels are not perfect, we might be then going back to clinicians and telling them things that might not be completely accurate. The final motivating example that I wanted to tell you about is a different one, because here labels are really, really good. So this is patent classification. And the way that is done is that we have experts, and amazing experts in this case, that would read the patent itself and categorize it as belonging to a tree that contains these 8 sections, 130 classes, and more groups and subgroups and so on. And even if the experts are amazingly good, just the sheer volume of classes and subgroups and so on makes the classification task very difficult for them. So it means that they might forget labels. And in some cases, it might be even impossible for them to just say whether something belongs to A or belongs to B. So in this case, we can trust the labels very much, but still, they are not perfect. So for all these problems, inside the machine learning classifier, we can try to address them to make the predictions that we produce better. So most of the work that we did in the last 5 years tried to formalize all these problems that are relatively close, but not always the same, and for them to have a common formulation. I won't go into a lot of details in the talk, but there is some notation in the next couple of slides where I try to simplify things as much as possible, and I assume that we have an input x, so this random variable here. There is a true label that we don't have access to, y, that we represent in this graphical form as a vector, where the black area is the label of interest, and the rest are not present. And z is the weak label that we do observe, that in this case, as you see, comes as an extra label that is given to us apart from the true one. So somehow it's quite an informative vector still, but there is something here that we need to understand how to deal with. The learning problem is then based on a data set of pairs X and Z, so input and a weak label. And there are two other objects that we need in order to characterize these problems. So one is the posterior probability of a true class given the input sample that we refer to as eta. And the second is an element that has many different names that we tend to call mixing matrix, this capital M, which is a matrix that tells us about any distortion that happened in between the true label and the weak label. So it's a stochastic matrix that is trying to encode any possible transitions, if you want, that have occurred going from Y to Z. So if we had information about that, we would understand fully how is that we went from clean and nice labels to just have something that is imperfect. So this object here is made of elements where each element, and we'll see examples in a second, is the probability of a weak label given the true one. So our task in the end is going to be to try to predict the true label without knowing what happened to our labels and given a sample. If we are able to do that, then we are in business. Just to give you a few examples, of what this means in practice, we can consider the case of noisy labels, where we start from this is synthetic data. So we have on the left here, we have 3 classes that I generated that contain, or in this case, I'm showing the true label. So this green, brown, and pink that happen to go through a box that distorts the labels. And what I get as Z, as what I'm going to use to train, is a version of what I had above, but changing some of the colors because I have flipping noise. So with a probability, I change the class that the point belongs to. If I summarize this as a mixing matrix, what I have is an object that in the columns has the true labels, so 3 in this case. In the rows, I have all possible weak labels. And to incorporate this idea of noisy labels, we have a parameter beta. And you can see that if an element of this matrix tells you the probability of observing a weak label, for instance, this one, given the true label, if beta is 0, then what I get is the standard supervised case. The higher beta, the more noise, and the more difficult potentially the learning problem is. Interestingly, in all these problems in practice, there is a big issue with this number of rows growing exponentially with the number of classes. So this object becomes very difficult to handle with even mid-size number of classes. Another typical example would be semi-supervised learning. And here the matrix has changed a bit to reflect that semi-supervised is a bit different, because now we have 3 parameters. And of course, if the parameters are 0, we are still in the supervised case. But if, for instance, alpha is larger than 0, what I get is that there is a probability alpha of me seeing no label when the true label was class 1. I represent the same thing on the left by using the same synthetic data, but after this transformation, I have some samples here in white for which I don't have the label anymore. Now, the final case that I wanted to illustrate, because it's a very common one, is a situation where what you get as Z is a pair of classes, and you know that one of them is true, but the other one is not. So your weak label always contains a true label, but it also contains something else. An example of this would be what we saw in the image with the 3 Formula 1 drivers. So I know that each instance is one of the three. So I know that the true person is in there, but I also get two other names that might not be relevant. I illustrate this on the left by taking the same data and then showing that in some of the cases, I have two labels, and one of them is always the true one. So for all these different scenarios and more, because this type of formulation also allows you to deal with problems like multiple instance learning or learning from label proportions and so on. There are solutions that are specific to each case. And also there are common sense solutions. For instance, what people used to do 10 years ago was that if I knew that a certain label was noisy, let's say, when learning, you would have a weight for that sample that would reflect that you trusted less. And that way you would trust more samples that you know are not noisy. However, this was very ad hoc, and what we've been trying is to come up with, first, general methods to address this problem. Second, that they have warranties so that we know exactly in which situations we can learn. And third, the design and choice of loss functions that you could put into any CNN and being able to forget that your data is noisy anymore or is weak. So in this sense, and I think this is almost the last time that I'm going to show notation of this type, the general formulation that we came up with is based on assuming that there is such thing as a scoring function that then through an operation I will turn into a prediction. But this allows us to talk about loss functions and their role in this pipeline. So here I need two extra elements. One is the conventional loss function that I refer to as psi tilde. I use the tilde for the standard one because we are interested here in the weak version. But you could think of this psi as a function of the score and the true label. And in general, this could take the form of exponential loss, square loss, anything that you're familiar with. And we tend to represent it in vector form for to make things more complete. But it just means that I'm evaluating here against all possible true labels. And the counterpart would be what we call a weak loss. And a weak loss, instead of being a function of the label and the score, is a function of the weak label and the score in the same fashion. And in this case, I call it psi. And our task is going to be to try to minimize this loss over all the examples that I have. And this loss would be the weak loss. And of course, it would have as an input the weak label. And as promised, this is the last time that I show this type of horrible notation. But what I want to summarize in this slide is the fact that there are results that tell us that the same properties that we can achieve for a standard loss, for the exponential loss or log loss or cross entropy, we can achieve for the weak version of those losses. And this means the following. Losses like cross entropy belong to what's called the class of proper losses, which is an amazing property that tells you, if you haven't seen it before, that if you're able to minimize it, the minimizer, the best possible solution would be the best possible classifier. So in a way, they are giving you a warranty that is not always useful, but it says that if you had the true model, it would be the minimizer of that loss. And what we found in this slide was a result that says that even with weak and imperfect labels, if I'm using a weak loss with that property, I will be able to learn always, regardless of what the distortion is. And the extra ingredient that this slide is giving us is that the relationship in between the cross entropy, let's say the proper loss for clean labels and its counterpart for the weak case is given here by this psi tilde being the standard loss, M being the mixing matrix that characterizes the mixing process, and this being the new loss that we'll have to optimize. This is really nice because it basically says that if I knew M, if I knew that I want to do cross entropy in my CNN, the only thing that I need to do is to replace cross entropy with a weighted version of cross entropy and weight it according to the inverse of M. Two small issues here, and two actually really important issues. One is that, of course, we don't know usually what's happened to our labels. So we don't know M. The approach to fix that one is that we can estimate it, and I'll show you how in a second. The second issue that we have is that even if we know M, because of the nature of this matrix, when you take the inverse, you'll end up with an infinite number of solutions that are not always easy to navigate. But the good thing is that if I knew M, we can do really cool things. We can combine, for example, data sets for which we know that the quality of the labels is different. And we can learn from all of them at the same time and have warranties that will find the optimal classifier. We do that, for instance, here, in a case where we have a data set that is noisy that we call M1, and we have a data set that has clean labels that is using this identity matrix here. We build new mixing matrices that are able to combine the two and learn optimally. Of course, as I said, this only can happen if you know M. If you don't know M, the obvious solution is to ideally have a set of clean labels that you can use only for the purpose of estimating the mixing process, and then assume that that's as good as it can be and see how it works in practice. We've done this in with traditional image datasets, of course, the ever-present MNIST, but also in CIFAR-10, for example. And what we tend to analyze in these cases is what happens as the number of training examples goes up that you have in the x-axis. And what we have is the upper bound of the fully supervised case in classification. So that's as good as we can do. And we have a lower bound, which is let's not do anything about the imperfect labels. Let's just assume that they are perfect and live with that. And that's what we get here in the orange line. Then the rest that you see in here is another upper bound, which is the green one, which is let's assume that we've been given the true mixing process. The red one is basically working with the estimated mixing process, which is a bit worse. And the blue one is a method of the state of the art, which actually was state of the art just before us. But in general, the potential of using this type of information within the machine learning classifier is limited by the two things that I mentioned. One is that we tend not to have access to the mixing process that distorted our labels. Two, even if we do, it's not always straightforward to find a way to select the correct matrix M. So with this, I've tried to summarize the common approach to how to address the presence of imperfect labels within the machine learning classifier. However, now I'm going to move to something that might seem different, but that will be the inspiration for us to do new things, which is basically to assume that at least for us, the least interesting part of the machine learning pipeline happens to be the machine learning model itself. And we think that most of the work that needs to be done in the next few years happens just outside. And for that reason, I will explore more the role of this human in a few slides. But I'm going to focus now a bit more on the role of this explainer that tends to come after the classifier, and see what happens with imperfect labels and imperfect predictions there. So for people that have seen explainability before, this is going to be the quickest of summaries. For people that haven't seen it before, then I hope it's a good enough introduction. So in this part of the pipeline, we assume that a black box model has been given to us, and we want to understand what's been learned, basically. And for that, we can go down the path of having interpretable models. Oh, sorry. If we use deep learning models, that's not always an option. So we have two alternatives, which are surrogate explanations and counterfactuals. Surrogate explanations are basically local approximations of a complex model that tend to provide some sort of insight of a specific example and how it's been treated by the classifier. So a very popular method is what's called LIME. And this method takes a picture like the one that you have there with the frog. And we tend to assume that that pixel has been divided into superpixels, so into meaningful sections of or areas of the picture. And what we do in order to try to explain what's going on with it and its prediction is to create a number of perturbations of that image, and then train a linear model and use the weights of those of that linear model to explain what's going on. So basically, this local approximation of something complex is assumed to be true when it's done locally. And with images, the explanation is not just shown as the weights of the regression, but as the superpixels that made the system, the machine learning system, decide that that was likely a frog. So this has attracted a lot of attention, but of course, it's not without issues. So you'll see that there are many methods in the literature, and depending on, for instance, the type of local classifier that you use, depending on the type of perturbation that you consider, whether that's uniform, whether that's constrained within a small area or a bit larger, you get, like in this case, these are 6 examples of different explainers producing very different approaches to what's an explanation. And when you see this with a concrete example, like in this case, with data from the adult data set from UCI, you see that 2 explainers on the same example produce drastically different predictions. If you see the y-axis, the features being picked by each of the explainers are completely different. The first one goes for capital gain. Education relationship has been really important as compared to the second one that focused on education first, but then age or occupation. So it's very difficult to understand really what's going on in this area. And that motivates other approaches like counterfactuals that I'm going to mention as quickly as I can. So in counterfactuals, you want to answer the question of, why wasn't my loan approved if this was a binary classification task? And usually what you want to achieve is that if I'm from class A or class 1, can you give me the closest point in class 2 that in a way I will understand as my counterfactual because it's very close to me and belongs to the other class. So an example of that would be trying to explain the X in the picture and then returning A as the first point as soon as you cross the boundary of a classifier. Some people claim that actually what you should do is to return B because that protects you a bit more to small changes in the decision boundary. And in a recent work, what we claim is that it might be better to return C or D, as those happen to be in areas where there is density. And density usually means that it is more likely that the advice that you're given by the counterfactual is feasible, so that you can achieve those values in practice. And actually, we argue for D as being the preferred option, because there are paths that you can follow to turn your loan application, if you were X, to an accepted one by going through a path of high density in the feature space. So these we can illustrate with MNIST by saying, let's start with a 0 and see how to turn that into an 8. But please do that using a path that has high density. So we try to understand the manifold and move from one point to their counterfactual. So now going back to weak and imperfect labels, here the situation that we have, for instance, with surrogates, is that we've been given a model, a black box that we want to explain. We don't have access to it anymore in terms of being able to retrain it. But given an image, I can put it through that model and see what the prediction is. So that's the only thing that I'm allowed to do. And we've been exploring recently what happens if, for instance, images from CIFAR 10, you add a small distortion in the form of noise, and you put them through the same black box. Of course, the black box hasn't been trained to deal with noise, but you would expect that if the noise is small, so that for a human it's not an issue, the explanation of why, in this case, that was a desk, should remain the same. So visually, in the examples that I'm showing here, any human should be able to see that the two images are basically the same. However, when using any of the existing explainers, what you get is that the superpixels that are highlighted as being important to explain that that's a desk, they change dramatically. And what we did was to address this in the fashion of a weak label problem. But now the weak labels come from the black box model that we want to explain. So we have the noisy images with the predictions that we assume are weak labels for that task. And what we can do is to apply all the theory that I mentioned before to unravel those and then get explanations that are robust against distortions. And we achieve this by playing with the loss functions in the explainers. Just because I'm aware of time and I want to be good and try to finish in 35 to 40 minutes, the final thing that I'm going to do is to look back at some of the things that I've mentioned and tell you just a bit of what we are currently doing. So we are back with this machine learning pipeline, and we talked briefly about the machine learning classifier and how to try to do learning there and training when the labels are imperfect. We talked briefly about explainers and how we can still do the same thing in there because they are nothing but classifiers usually. And the last thing that we are doing these days is to try to see what is that we can do in this part of the pipeline. So what happens before the machine learning classifier? So there, what we try to do is to be a bit less ambitious and not try to estimate this mixing process, this distortion process that happened to the labels, but to give users tools so that they can test their assumptions on labels. So for instance, if I know that because of the way I labeled my data set, I used a mechanical Turk, and I know the type of annotators that I got, and I know the type of images that I'm giving them, I might have an expectation of how good they will be on the task that I want to test later. So what we do is that we design hypothesis tests to assess label quality. And the way that we do that is basically the same as in the explainers that I was mentioning before. So we assume, because we always still have to make an assumption, that we have some information about what's true. So in the previous slides, at some point I said we might have some information about clean labels. In here, I'm assuming that we have some information about the posterior. So we have a user that is able to tell us something about either what's very uncertain or what's completely certain. And we turn those into surrogate models that we compare against the labels that we have. And that way we can return a response and a p-value saying, we think that if your assumption was that there was a flipping noise of this rate in the data, we think that that is correct. So that's the direction that we are moving these days. And the final thing to say is that this is all being done as part of a Turing AI fellowship, which is a 5-year fellowship from the UK government, and in which we are interested in all aspects of human-centered machine learning and AI, and particularly in ways of giving feedback to machine learning systems using labels and annotations.